So let's go over the bonding 7 intermolecular attractions worksheet. Let's do it. So I'm giving you these structures, and normally they're giving to you in a way that you can understand them better, but these little line structures, the carbons are actually at the corners here, and they would be H's here, so this is not how you would see it. Okay, but fun to look at, sure. So this is butane, okay, and all these carbons are sp3 hybridized. All right, and the reason for this type of arrangement is to show that kind of sp3 tetrahedral structure, but it's also showing us the similarities and similarities of the structures, which is important in terms of polarization. In any case, just putting in the carbons here, and this would be, again, CH3 at the end. This would be a carbon. This would be a carbon with CH3 at the end, and this would be 2 H's. And this would have 3 H's. And again, just drawing this so you can visualize the structure, but where I put the black, all right, is to show you that's the carbon backbone. This is a CH3 at the end, and this is a CH3. Okay, here comes the question. We have butane boils at 0 degrees Celsius, methyl ethyl ether at 8 degrees Celsius, and acetone at 56 degrees Celsius. So the question is, explain the trend in boiling points. Now we talk about boiling, let's not forget we're talking about how butane attracts another butane molecule. So if you think about this as a butane molecule, how does one butane molecule attract another? And if those attractions are weak, then if I have liquid butane, these butane molecules will easily become a gas. Okay, so if you look at, it has the lowest boiling point, which means it requires the least amount of energy for these butane molecules to create a vapor pressure upward that matches the atmospheric pressure from gear. So boiling, of course, is when the vapor pressure upward equals the boiling point downward. All right, very important. So we would say that butane clearly has the weaker of these attractive forces, but that's not enough here. Okay, really what these questions are after are in terms of intermolecular attractions between the molecules, explain why. So the first thing I would say is that, well, all three of these have a cloud of electrons. So these all experience these LDF forces, London dispersion forces. So I'm going to write LDFs for all of these. And London dispersion forces are those forces where clouds of electrons, okay, move just very slightly, okay, which is called polarizing, in the presence of other molecules, electrons or positives. Okay, in any case, these all have LDF forces because essentially they all have clouds of electrons. Now, if we look at the little box they gave us here, notice they gave us the total number of electrons, and essentially the electrons are essentially even. Now, why do we do this? Because we know polarizability, and that's a really important term, ability. Very important term, something you want to put in your back pocket. And we know that if we have more of these electrons in our nonpolar molecules, these electrons, if you have more of them in a, if there's another negative here by another molecule, polarizability is the ability of these electrons to slightly move. In this case, they'd move away a little bit. Why? Because they're repelled by these electrons. Now, they don't move that much. So that's why these are weak forces. And of course, if this negatively charged ion, particle, or part of another nonpolar molecule were to move away, okay, these guys would move back. All right, but the more electrons you have, the greater the ability to create a negative side and a lack of a negative side called a positive side. So these all have the same number of electrons, so it cannot really be about polarizability of the number of electrons. And if you notice, they have very similar shapes. And how do I know? Again, going back to the backbone here, very similar shapes. At least these two do. These do not have very similar shapes. Any case, getting back to the way that I would answer this, I would say that essentially they all have LDF forces. And I know that because of this O right here and this O right here, these guys are polar molecules. So they're going to also have dipolar forces. So one thing I could say, the reason why butane is going to have a lower boiling point, which means weaker attractive forces, needs less heat to vaporize and match the atmospheric pressure, is because it only has LDFs, while the other two molecules have LDFs and dipolar forces. That would be the best way to explain this. Notice how I said this. It has LDFs, and while the others have LDFs and another force. Remember, the additional force is a cumulative effect. So we always talk about the idea that, yeah, they all have LDFs, but these two actually have an additional force added on top of the LDF will make it have a what? Stronger attractive force, which means it won't vaporize as easier, which means it needs what? More energy or more heat to boil and a higher boiling point. Okay, so that's the first thing I would say in terms of butane. The other two have an additional attractive force on top of the LDF. Okay, second thing, now why would methyl ethyl ether and acetone have so far different boiling points? Well, the one thing we look at is the shape is not the same. So if we look at the LDF forces of acetone, we could probably understand that we have what? 3 carbons here. Now go look, acetone actually has less electrons, but again, they're very similar, so you can't look at the electrons. So let's look at the shape. Acetone pretty much is kind of a circular, when you think about more circular or branched than this. So its LDF forces, okay, are probably going to be actually weaker, okay, than the LDF forces of methyl ethyl ether. You're like, what? Yeah, probably. But that doesn't answer our question very well, because if the LDF forces are stronger here, then you'd expect to have a much higher boiling point. So what gives? Okay, well, what probably is the winning answer here is that because of the shape, because of the fact, and I'll just pick a nice color here, this oxygen has the ability to pull electrons this way and pull electrons upward to create a real negative permanent dipole. The dipole moment for this is very strong. So as compared to this molecule where the O is kind of in the plane where the carbon was, it's still sp3 hybridized, so it's kind of in the same plane. It doesn't have the same ability with its bond angles to make a pure dipole moment. So this one has a much higher dipole moment, which means it's more polar because of the shape, and therefore its dipolar forces are much higher than the dipolar force here. So the best answer for why acetone really has a greater difference of I would say, of a boiling point is because its dipolar forces are so much bigger, okay? That even overtakes the fact that its LDFs are actually probably going to be a little less because of its shape. Remember, polarizability is due to electron number, which is, and also the shape. If something is more elongated or a long chain and non-branched, it's easier for these electrons to move to one side to create polarity. So this question wasn't really about that, but I'm going over it. Really the best answer is the dipole moment, or the dipolar forces of acetone are much greater than that of methyl ethyl ether. It's more polar because of its shape and where the O is. That creates a much larger boiling point, okay? And that's how you would talk about it. Again, try to mention all the forces. Okay, if I was talking about methyl ethyl ether and acetone, they both have LDFs, they both have dipolar, but it's really the dipolar forces that are so much more different in the acetone. They're so much more greater because of the shape and the way this creates a more negative side of the molecule. Okay, all right, so any case, let's move forward. All right, now this is pretty awful question here, and I'll just basically touch on it a little bit. So I'll give it my best. Which of the following systems will hydrogen bonding play an important role? Okay, well, we've got CHF, all right, and again, these are probably written out a little better for you. And then we have what? We have the CH3 thing and a CO. What that means is you have the two CH3s to the what? Carbon that's double bonded to the O and to the CH3. It's the acetone, as you keep seeing. And then we have NH3, which has got that lone pair, and it's got that tetrahedral shape, at least for all of its electrons, trigonal pyramidal, pushing down, and then dissolved in, what is this again? CH32CO, it's again acetone. So what I'm saying here, hard to say, but which of the following systems will hydrogen bonding play an important role? Well, this compound right here has no ability to actually hydrogen bond with itself. But, okay, if you have acetone right here, acetone has no ability to hydrogen bond with itself as well. In fact, these two elements, or these two molecules, do not have any electron deficient H's. Hydrogen bonding is when, of course, you have a hydrogen bonded to the most electronegative atoms, which could be F, could be oxygen, or nitrogen. And because these guys have high effective nuclear charges, or electronegativity, if you want to think of it that way, they're pulled in close, and you're left with this very important idea, electron deficient H. All right, and being deficient means its electron is pulled so far away, you're just left with the nucleus. We all know that hydrogen, being that it has a mass of 1 and atomic number of 1, is 1 proton and 1 electron. Well, party people, okay, if you take away the electron, it's just a proton. So H bonding essentially is a scenario where you have this FON or FON type of a molecule, so F, O, or N, pulling that pair of electrons so much, you're just dangling a little proton out here. And if you take the shape of this little proton can attract very strongly another electronegative atom to create a very strong attractive force. And that's what we call H bonding. It's a terrible name because it makes you think about the bonding. But if you look very carefully, there are no H's here bonded to an H, an N, or O, or an F to create this unequal sharing to have this electron deficient H. So none of these guys can H bond with themselves. So there's no H bonding within these. Remember, these H's are hooked up with these carbons. However, okay, if you've got ammonia, ammonia is one of the 3 most electronegative elements. So these electrons are being pulled so close. What ammonia has, and you think about it, it's got these little protons sitting out here that are highly attracted to other things that are very electronegative. Hello, oxygen. Hello, fluorine. So although acetone and this molecule here do not H bond, okay, ammonia would definitely H bond with acetone, and ammonia would certainly H bond with CF. So they don't bond or H bond with themselves, but how would they be involved in H bond? Well, if I redraw this molecule, C with the F, and really when I do the Lewis dot diagrams, I should have the lone pairs, but hey, so I have this, and then I have my H's. And how would this H bond? Well, the N, draw this upside down, is going to give off an H, and those H's are really dangled protons, and certainly this very electronegative here is attracted to this proton, or this proton is attracted to this very electronegative atom, and there is your H bond. It's not a bond, it's an intermolecular force of attraction that's very strong between essentially an almost free proton and a very electronegative atom, which itself is pretty darn negative, and that makes a very strong attractive force. H bonding is how DNA is held together, and certainly we need it to be held together, okay, to keep our genetic information. And certainly there are many forms of H bonding polymers that are important, especially bulletproofing H bonding polymers. Kevlar is one. So how else would H bonding occur? Well, look at our acetone. Acetone, and I'll just draw it right here, C CH3 to this CH3 to double bonded O, and this is an H from the end, so there is another H bond, and we call that an H bond. So although acetone cannot H bond with itself, it can form an H bond because of electron deficient H of, in this case, ammonia. Okay, so moving forward. All right, my favorite part is this one right here. So explain the following differences. All right, so let's do A first. All right, we got krypton, and then we've got propane. Now, propane is actually 3 carbons, and I'd give you the structure, and then you're going to have all H's surrounding it, okay? And let's just put them there. So it's a hydrocarbon. We know it's nonpolar because the hydrogens and carbons have about the same attraction for electrons. And krypton is, of course, one of our noble gases. We know it's non-reactive. Okay, at least not around fluorine. Any case, what do I know? Well, they both have LDFs. Why? Because they all have what? Clouds of electron. Everything's got LDFs. But now why does krypton boil at negative 152, and why propane boils at negative 42? What's the reasoning here? Well, this has a higher boiling point, propane, because it has what? Stronger intermolecular forces of attraction, IMFs. Okay, a little catchphrase here. Why is there stronger? Well, they are not polar, so this is the only attractive force they have. So it must mean that propane is more polarizable. Okay? Now, what's polarizable mean? It means that the cloud of electrons can easily shift to one side more than another in the presence of an ion, another molecule, or so forth. Now, if we look at krypton on the periodic table, we can see it has its atomic number 36. So if it's atomic number 36, party people, that means it's got 36 protons, and it has what? 36 electrons. Okay, well, how many electrons do I have here? Well, each carbon is atomic number 6, so 6 times 3 is 18, plus 19, 20, 21, 22, 23, 24, 25, 26. So 26 electrons. So you might expect, hydrogen is atomic number 1, so 1 electron there. You might expect because there's more electrons in krypton, it's more polarizable. But that doesn't explain why propane, sorry, is so much higher than krypton. So that doesn't really mean anything here, or that number of electrons is not causing krypton, or doesn't explain these differences. So something's going on here. Well, the only thing we can think about krypton. It's an atom. Compare an atom to a molecule with a bunch of atoms. Look at the relative sizes. This has a bunch of atoms here. This is one atom. If so, I have 36 electrons stuffed in a small place, and I have 26 electrons spread out over a longer place. Who do you think is more polarizable? The propane, because these electrons, although spread out and more diffuse, okay, because of their elongated shape, okay, not branched, these electrons can actually move and create an electron deficient area or electron rich area. Remember, they slightly move better than this very dense, great number of electrons in this small area. So because it's circular, okay, it's non-polarizable, and so because it's so small, so it must mean that B has a higher what? Boiling point, because it has stronger LDF forces due to greater polarization, because the electrons are more free to move along this bigger, longer molecule. So in this case, it's not about the electrons, it's about the shape, okay, and the ability for electrons to move a little bit. They don't move a lot, but in this shape here, they've got more freedom and space to move a little bit, whereas an atom being so small, those electrons aren't polarizable enough to create an area, okay? So that's why B is the answer. Let's go after choice B now, or let's go after the question B. All right, so in B, what we have is CCH3 boils. So that looks like this, carbon in the middle, bonded to a methyl group. All right, and again, these structures would be given to you. This actually is bonded to the carbon, but hey, that's fine. All right, now it boils at what? 10 degrees Celsius. And then we have carbon tetrachloride, CCl. And I should put the dots around the chlorine. There's 3 lone pairs. Okay, now notice the shape is similar. What does that tell us? Well, the shape is not going to be a factor in the polarization here. Now, if you look at, this is 77 degrees Celsius. Now, the first thing we look at is say, okay, what kind of attractive forces do these have? Well, because of symmetry and the dipole moments canceling off, these are both nonpolar. So they're going to all have LDFs, or only have LDFs. There's no polar or dipolar forces or H bonding to go here. So it really is about who has greater LDFs. And LDFs increase because of polarizability, or the distance of how one of these molecules gets closer to another. Now remember, boiling points are about how well this guy attracts its own molecule. This boiling point is how well this guy attracts its own molecule. So clearly, having a higher boiling point means that this one has the greatest, strongest intermolecular forces of attraction. In this case, it has stronger LDFs, but that would not be enough to answer this question. Why are the LDFs stronger? Well, you can think of it 2 ways. Well, actually 1 way. Number 1, this has to be more polarizable. This must have an ability for electrons to move to one side or the other. Now, if you look at the shapes are exactly the same. They are tetrahedral shapes, so the shape isn't going to win over. So it must be about the electrons. Think with me, party people. Chlorine, atomic number 17. There's 17 electrons for every one of these chlorines. Okay? How about one of these? There's 6 for the what? Carbon, and then 3, so there's 9 on every end. So you can clearly see having 9 electrons on every end and 9 in the middle. Okay? This compound, carbon tetrachloride, has more electrons with the same shape, is going to be more polarizable because of a greater number of electrons. Okay? And having more electrons in my electron cloud for the same basic shape means what? When there is a compound, let's say that's positive or an ion, these electrons can do what? Move. There's more of them to move, which creates a greater negative area, and a place that lacks the negative, a greater positive area. Remember, these are momentary charges. All right, so let's go on to C. So letter C, N2 boils at 196, liquid nitrogen, yes, okay. And carbon monoxide boils at negative 191.5 degrees Celsius. So what's going on here? Well, let's ask the questions. What type of intermolecular forces do they have? They both must have, no matter what, LDFs. They have clouds of electrons. This has no polarity, no H bonding. This is polar, so this has dipolar forces. There's no electron deficient H's, so it doesn't H bond with itself. Okay, so if you look at the reasoning here, negative 196, negative 191. Clearly, okay, this is the higher boiling point. It's got the stronger intermolecular attractions, IMFs, of forces of attraction. Why? Because, and this is how you would say it, carbon monoxide, like N2, has LDF forces. However, it has an additional force of dipolar forces on top of the LDF that gives it an overall stronger intermolecular force, which leads to a higher boiling point. So you've got to mention both. You have to mention that both. You just can't say, hey, carbon monoxide's polar. And it is. Okay, it's got some polarity. Okay, see there's a difference here. There's a difference here. And of course, it's not as polar as we think because carbon monoxide actually resonates. But the point is, in this question, to keep things very simple, carbon monoxide has one more additional intermolecular force than nitrogen, and that is dipolar forces. And that's the way to answer this. If you were to say, hey, carbon monoxide has dipolar forces, you get it wrong. You'd have to say both of these have LDFs, but carbon monoxide has an additional. You have to mention the fact that you recognize the fact that the reason why there's a stronger intermolecular force here is because of the cumulative effect of all the forces CO has. All right, so you've got to mention it that way. All right, so let's go on to number 4. Assume methanol and acetone have nearly equal boiling points. Well, methanol, let's do acetone. We've seen that before. Acetone it's a ketone actually, but it looks like this. Very important solvent in organic chemistry. And we have methanol. Meth is a 1-carbon alcohol. Okay, and the alcohol looks like this. Again, these shapes will be given to you. They have nearly equal boiling points. So their boiling points are dead heat here. They have about the same. What types of intermolecular forces do each exhibit? Okay, well, now when we're talking about the forces they exhibit, we're always talking about to themselves. How does acetone attract another acetone? Well, they have LDFs, and so does this because it has a cloud of electron. Everything does. This guy's polar, so there's what? Dipolar forces. And this also is polar, right? So it has dipolar forces. But this has an electron deficient H, so therefore it could H bond with itself. So this has H bonding, which may bother you because you may say, wait a minute, how can these have the same or about the same boiling point? They're about 51 degrees Celsius, both about 51 degrees Celsius. How can that be if we figured out that the entire intermolecular force is due to the cumulative effect of all of its attractive forces if this has more? The only way to explain this is understand that these forces are not going to always be equal. Okay? So let's think about this for a second. The LDF force to this LDF force, clearly they're about the same. Now, dipolar force and dipolar force, well, that may be different, but let's take a step back. Notice this methanol has 3 forces, clearly has 3 intermolecular forces that dominate its intermolecular force of attraction. This only has 2. They have the same boiling point, which means they have approximately the same intermolecular force of attraction. The only way that this collective pair of attractions can equal the collective threesome of these attractions, one of these or 2 of these have to be bigger individually to overcome the extra H bonding force. So who do you think is keeping this, or in this case, so which one of these 2 forces is probably so much bigger than the other that it compensates for the extra H bonding? Well, when I look at this, as we talked about before, the structure here of this oxygen in this sp2 format, this oxygen can tug on these electrons and tug on these electrons and really create a very electron-rich area. Acetone is going to have a higher dipole moment. It is more polar because of that structure. I could give you dipole moments, or you have to recognize that. Here, yes, oxygen is yanking on these electrons a little bit. Because of the differences in the structure, okay, this is a 109 bond angle. All right, these are 120, so these electrons are more in the same plane to be pulled. These can't really make a right turn as much. So these electrons aren't pulled as much, even though this looks like in the same plane, it's not. So these electrons can't be pulled upward to create a more electric-rich area, so this dipole moment is less polar. And that's your answer, okay, is essentially that acetone has great enough or such a big dipole moment that it creates such larger dipole forces that it compensates for the fact that it doesn't have H bonding. So the dipolar forces are so much bigger in acetone than in the methanol that it again can have the same similar attractive force and thus boiling point, even though it doesn't have H bonding. It's more polar, okay? The LDFs are kind of tough to figure out. And you may say also, possibly the LDFs are bigger, but hard to go there. These both have very similar rounded shapes. And well, probably you can think that this has more electrons, right? You have 3 carbons and an oxygen. So you can probably make the case that they're both the same shape. So the shape's not going to be a factor. This actually has more what? More electrons. 8 plus what? 6 plus 6 plus 6 more for that is going to be greater than the what? 8 plus 6 plus 4 more. So this is a larger number of electrons. So I can make the case that the LDFs are bigger here, both with the same shape but more electrons, like we talked about the carbon tetrachloride above. So the LDF is bigger, the dipole moment's bigger, and because of that, that difference can compensate for the extra H bonding, and that's why they're the same. All right, so moving on to the last question, good times. All right, so we've got a neighbor of arsenic, germanium, melts at 120. Now, to just understand how this works, what we have is we have boron, carbon, we have nitrogen, oxygen, fluorine, okay, all right. And now under boron, we have aluminum in row 3. Okay, we've got silicon, we have phosphorus, okay, we have sulfur, we've got chlorine, okay. And then, of course, in row 4, we have gallium, germanium, arsenic, and selenium. Oops, selenium, just Se. And then bromide. So we're, okay, this is the halogen 17. Now, you think with me for a second, okay. Gallium is next to zinc. Okay, zinc is next to copper, and these are our transitional elements. So if you notice with me, we have our what? Our metalloids, kind of separating our metals here from our non-metals over here, right? The smaller high effective nuclear charge elements. Okay, so non-metals. All right, and so what's our boiling points? Germanium has a boiling point of 1210 degrees Celsius. And then selenium is down to 490. What gives? Well, what you should understand is the differences in the types of solids that we have. So the solids that we have metallic, and these are bonds between metals. So if I have iron is, I think, a body-centered cubic structure of iron nuclei. Remember that C of mobile electrons. That make crystals. Okay. Then we have ionic, is where you have ions in crystal, like sodium plus to chlorine negative to chlorine negative to Na plus. Then we have molecular solids. Now, molecular solids are just what we talked about, molecules who attract themselves either by LDFs, dipole, or H bonding, or all 3, or 2 of the 3, or just 1. These are attractive forces, and generally speaking, they don't make crystals, and these attractive forces are going to be so much weaker than the forces of attraction in these 2 crystals. So molecular compounds, they're going to have much, much lower melting points. Metallic compounds and ionic, because of the crystalline structure, and of course metallic has these electrons that are able to flow throughout, and be attracted in all directions, hard to break. So these are going to have incredibly high melting points. So if you look at germanium, even though it's a metalloid, it's got a lot of metallic character, it's going to exhibit metallic bonding, And so would a molecular fall under 490? And of course you would say no. Molecular would be like butter, or plastics. or even ice. Ice is considered to have, or water in the solid phase is a molecular solid. Remember, this is metallic solid, ionic solid. Molecular solid would be like water in the solid phase. And for its molecular mass, it has an incredible melting point for its light mass, but it's only still 100 degrees Celsius. So something with a very high melting point for a molecular solid still are only around 100. This is way above that. So what is the other form? Well, there are a few exceptions that exist for molecules, or this I should say non-metals that live in this range here, that actually make covalent bonds in all directions. And those are called network solids. So we have metallic, metals to metals. We have ionic, usually metal, non-metal, transfer to make the ions in a crystal. We have molecule or molecular solids that usually don't make crystals. They're just stuck together by attractive forces, like ice sticks together because of H bonding. Okay, and of course dipole attractions, and some, of course, LDFs. But essentially, that's pretty low. Network solids are where we have, for instance, diamond, carbon, bonded like a tetrahedral in all directions to other carbons who are bonded in a tetrahedral. And it goes on. And it's a crystal pattern of what? Of covalent bonds. And because those are bonds that keep the crystal together and not attractive forces for molecular solids, these are going to have higher than normal boiling points, but nowhere near as high as metallic or ionic, okay, that are in real tight structures with a lot of electrons, okay? So this is going to be a network solid. All right, hope that helps.